Hey there, thanks once again for tuning into CMTEQ channel. Now this is part 3, okay, for the previous tutorial where we did a binary counter. Okay, so this is STM32 programming using the nucleo board. Now in this part 3, we basically just going to not tweak but change the way we are addressing our microcontroller. Now in this code here, as you see here right now, I've just made a copy of the previous part, right? So in this part here, we basically were using the HAL libraries. As you can see, we are basically just calling functions and passing parameters and doing the things that we want to do. In that, we basically just achieve the binary counting up and counting down and also the sequence of light running. So in this part 3, we basically going to bypass these HAL libraries, and we're going to use what is also known as a bare metal programming. In other words, direct register access. So by direct register access, what we mean by that is we going to make use of the C compiler, right, which is a low-level programming language, to write instructions that is directly going to access the registers of the microcontroller there and do the things that we want the board to do for us. Because the difference that now is we basically using a driver. Now the drivers is just a bunch of C programming functions, okay, that are making it easy for us to access the microcontroller by giving us functions that are humanly readable. Like we can see HAL GPIO write pin, we know that we are writing something into a pin. HAL GPIO read pin, we know that we are going to be doing some reading. So it's a human language. So these are the libraries, the functions that are written in the HAL drivers that we can make use of and make our life much easier. But now we're going to now try the hard way. Now that's just mean we understand our chip and we are able to talk to it directly without some other layers. So having said that, thanks for really tuning in again, and please subscribe to CMTEQ channel and give this tutorial a thumbs up if you find anything useful to it. So we're going to start by these two functions here. I'm not going to tamper with the delay function here. Okay, that's just going to stay because there is nothing in there, just basically C code there. So what I'm going to do here, so we're going to start with these two functions here that we are configuring, GPIO A and GPIO B. Now first off is this function, GPIO B configuration. In this function, we're basically setting the parameters for the two push buttons that are doing the business for us. Now, when you look at the first line here at 100, we've got the HAL drivers here that is calling the RCC GPIO B clock enabled. As its name implies, it is enabling the clock for this peripheral for GPIO B. So what we have to do, if we're going to replace this, we now need to go into that reset and clock control so that we can find that register and enable the clock as well, so that our code can continue to function. So I'm going to open the reference manual. Now when I bring out the reference manual, I come to here, number 8, reset and clock control, RCC. Now if I come on RCC 8.4, RCC registers, I need to find those registers on RCC. Now what I'm looking for is this register here, AHB register. That's the one. Now when I open it, you can clearly see this is a 32-bit wide registers, and I need to look for the specific bits that is enabling my clock, okay, for GPIO B. Now when I start counting from 0 here going all the way, and some of these bits are blanks, and when I come to 17, I see well, IOPA, that's PA, then IOPB, okay, this is port B and enable, so it's bit number 18. Now I know I need to enable bit number 18. Okay, now what's the story here on IOPB enable? So I have to come down here. Let me just come down. IOPB enable. Now when you look at IOPB enable, it says here bit 18. bit 18, and I've got 0, it means clock disabled. 1, it means clock enabled. So I have to set it to 1 if I need to enable that peripheral clock on the RCC control register, right? So the reset clock control. So I'm going back onto my code, and I need to call now the reset control. So that will be RCC, reset clock control. And then I'm just going to point the arrow and wait for the IntelliSense. Now the IntelliSense here for the GCC ARM compiler is already seeing that, okay, you want to access the registers onto that RCC. Well, here are the list of registers. Now, which one do you want? You can just go and look for the one that you're looking for. Now, I'm taking the top one. You can see that it is a 32-bit unsigned integer wide. So I'm going to just click in there. Now I'm taking that. So here, it means that I'm going to access that register. So now, what am I going to do inside that register? Well, inside this register, I need to write a 1 on bit 18. Now, in order to write a 1 on bit 18, I'm going to just say equal 1 and sign long in capital letter. That's better like that. And I'm going to shift by 18 so I can write that 1 into this register. So I'm going to shift what? Left 18 times. So if I shift left 18 times, and I'm going to write a 1 unsigned long into this register, that means the clock is going to be enabled. But what, I cannot leave it like this, because anything else that is in that register is only going to contain this value here that I'm setting. So if there are other stuff in there, it's going to be override. So for me to allow that other stuff also remain, I need now to use the OR operator. So I'm going to put a OR here. So when I put the OR here, that means I'm keeping everything else that is in that register the same, except I'm just changing bit 18 to 1 to enable my clock on that register, GPIO B. Now we're done on that first part. So which means we don't need this one here. So we can just take this one out. Now the next thing is to configure the port itself. Since now the clock have been enabled, now we need to configure this port as what? As input, because we've got buttons in there, which means it must be configured as input. There it is. We're doing it here with the library of the drivers, the HAL libraries. We were doing the mode and we say mode input. Now we're not going to be doing this anymore. So how are we going to now enable the mode? Well, we need to access this register also now on the GPIO B so that we can see how we're going to put it to mode input. Now let's go back to the reference manual. Now I'm in the reference manual, and well, here we need to go to GPIO B or GPIO port, and I can see number 9 here. And here, if I click on 9.4, I'm getting all my GPIO registers. And the first one here, obviously, is register model. So that is the mode for the register. And this one here also is 32 bits. Now, in this register, there isn't much going on here. There is only basically 4 functions here. So there is input mode. That's a reset mode. So as soon as you reset your microcontroller, automatically the pins are in the input mode. That's what it says, reset state. And 0.1, that will be general purpose output mode or alternate function and analog mode. Now we want to set it to input. That basically means just 0, 0. Now we are not using any other pin in this program on this GPIO B for any other function. We're only using the 2 buttons for input, pin 8 and pin 9. Now the 32 bits here, that means 2 bits will represent 1 IOs or 1 pins. That means 0, 1 here will be for PB0. These 2 will be for PB1 and so forth. So your PB9 and 8 will probably be somewhere here if you count right. So the story here is, since we are not using any of the pins for anything else, we're just using the pin 8 and 9 for input. So we can just write the whole register as input. So we just write a 0 to the whole register. That means all of them, they're just going to be inputs. But if you're going to use another pin in this register for something else, then you have to specifically set your pin 8 and 9 input and leave the other pins as is for other purpose, maybe for output or for alternate function mode. So now to set the whole register as input, you guessed it, we're only going to write a 0. So I'm going back into the code here. And when I come into the code, just on this line, what I'm going to write, I'm just going to say, well, I need GPIO B. Here is GPIO B, my arrow. And then I'm waiting for the IntelliSense to show me the options. There are the options. So the IntelliSense is telling me, well, here, this is what you have in this register. So I'm looking for the model. So I'm taking the model, and in here, I'm just going to say, well, I only want to write zeros on all of them. So I'm just going to write 0 like that. Hexadecimal, binary, decimal, it doesn't matter. It's still going to be just 0. Okay, so I don't need this. I can already remove it. So now the next thing here is basically to configure the pulls options for your input buttons, for your input pins. And that should be a pull down. Why is it a pull down? The reason why it's a pull down, because here I'm pulling them up. My buttons are already being pulled up to VCC or to 5 volt. So which means I have to pull them down internally so that when I press the button, the STM32 is now going to detect a high, because I'm now going to be pulling the port high, because it's already pulled high here. Okay, so I have to pull it down internally so that when I press it, I'm actually connecting the GPIO to a 5 volt. So I'm pulling it high. Now, why pull it down? Because if I leave it open without any pull, it's going to be floating. And when the pin is already declared here as an input, you cannot leave it floating. You have to now define it. You have to now pull it down so that it does not catch noise. So if this pin was floating, I might just bring my finger close by and then the button's already is triggered, because it may be detecting some capacitance for as my finger is approaching and all sort of parameters. So this is why you have to pull it down. So we are in the reference manual. Now we need to look for the pull down register. There it is, GPIO pull up, pull down register. There it is, pull up, pull down register. So in order to pull down, your pin must be 10, you must write, and the 01 is for pull up, 00 is for no pull. Right, so we want to pull down, so we need to write 10 into where? We need to write 10 into pin 8 and pin 9. So now we need to start counting. We need to start counting our pin. So if I go like this, so these two are GPIO B0, B1, B2, B3, B4, B5, B6, B7, and B8. So this is B8. Bit 16 and B17 are B8. Now if I write bit 17 a 1, I'm going to have a 1, 0, because this will be a 1, this will be a 0. 1, 0 mean pull down. So I have to write a 17, bit 17, 1, so that pin 8 is going to be pulled down. And then these two are for pin 9. Now pin 9, if I need to write it also pull down, then I need to toggle 19 here to also have a 1, 0. So now I've got my answers. I need to write, I need to shift 17 times and 19 times and write a 1 on each one of them into this register. And that will make pin 8 and pin 9 to be pulled down. So now I go back into my program. Now I come back in my program and I'm going to also access the GPIO B and then waiting for the IntelliSense. Now this time around I need the pull up and pull down. So it's that last one, pull up and pull down register. And here I'm going to also use the OR operator so that I want to leave everything else the same because I'm going to OR everything. And now I need to shift left 17 times to write a 1 unsigned long. 17 times. This is going to be for pin 8. And then I'm going to OR it. That means I'm adding another one. And then I write another unsigned long. Shift it 18 times. And this will be for pin 9. Now I can remove all of this. Now when I remove all of this, suddenly my function is looking very, very small compared to a lot of line of code I have. Now to prove to you guys that this should work, I'm going to compile it and then load it into the board. And if we've written the correct instructions, I should still get the same functionality. But if my buttons stop working, that means the configurations for the two buttons are wrong. Now let me write this now. We need this one, binary counter, direct register access. Now just observe. Now just observe, you can see we are loading there. We're connecting to the debugger. Now we are waiting for the debugger to finish the connections and to load the program. Okay, so now we wait for it to shut down. Okay, now it is done. It needs to shut down. Right. Okay, now what is going on here? I'm already counting down. You can see I'm counting down without pressing any button. That means something is wrong. So 17. Well, we said we're gonna write 17 and 18. Did we say we're gonna write 18 or 19? Let me just check here. It must be 19 to get a 1-0 because I wrote 18. That means it's a 0-1. What is 0-1? It's pull up. You see, it's pull up. So by writing 18 here on this button 9, because this is button 9, that's button 8. So this one is button 9. So which means it's already pull up. But it's only supposed to get a pull up when I press a button. So which means the button is already being pressed without me pressing it. Only because I already enabled a pull up instead of a pull down. So I'm going to change this to 19. And then we're going to run the code again. So I'm going to run straight. No ST link. Let me just reset here. And then we try again. Okay, so now it's done loading. We just wait for it to shut down. Hopefully this time around we're not going to have that that pull up enabled. Okay, shut down. Now we can see the code is quiet. Now when I press my button, now I'm starting to count down because it's now on pull down. But previously it was already on pull up when we had an 18 here instead of a 19. So you can see, guys, that the code is working. Okay, so the button for going up, which is button 18, is also working. And when I press like this, I'm also getting my sequence. So that means my buttons configurations have been done properly. So now we can move into this GPIO A configuration. And this code is to configure the GPIO pins where the LEDs are connected as an output. Right. Alright, so first off, on GPIO A, we also need to enable the clock register for port A. Now, looking into the register here, AHB, we can see that IO port A enabled bit is bit 17. So, which means all we have to do is basically just to copy this code here, right? Because in programming, you have to be able to copy the correct code in the right place to save you time, right? So we just replace that with 17, and that will mean the clock on port A would then be enabled. Having said that, we don't need this variable as well. Now the next thing is now to set our corresponding pins where the LEDs are connected onto GPIO port A. We can see that it's pin 4 up to pin 8. Now with the register direct access mode, the pins configurations are done with this register, model register. So that is where you select the pins, whether you're going to set specific pins as input or output. Now let's go find that register. Okay, so that is the GPIO port mode register, also known as model register. So now in this register, just like we've done with the port B, we selected pin 8 and pin 9 by setting this specific bit, as you can see it here. Now you saw here we use the GPIO B model register and we wrote a 0, so that was like a reset state. It set the pin as an input. But when you are setting bits as output, you have to use the same GPIO register and write specific bits output, so that those pins are going to be selected for output mode. Now the reason we didn't specify pins here, because we basically just wrote the whole register as input, because that is the reset state as input, and then we selected then the specified pins that we took, which is pin 8 and 9, and we pull them down so that we don't get noise on those pins where we're going to use them. But now in this case, since we're going to use these pins as output, we then have to specify to write the output state of the selected pins, which is going to be different than writing a 0 if we can just go into the register here. So GPIO port mode register, also known as model. Now as you can see here, 01 is for general purpose output mode. Unlike with setting the pin as input mode, which is a reset state, we just wrote 00 into the whole register. That means all these bits are going to be 0. Now if you just write 01 into the whole register, it's not gonna work. You probably just be writing the first bits here. Now you have to then assign 01 on all of them, and that's going to be a large number. No, we're not gonna do that. So we're only going to take the selected bits, the selected pins that we need. So that is pin 4, 5, 6, 7, and 8. 5 pins on GPIO A that need to be used as output. So having said that, bit 1 and 0 represent GPIO PA0. Bit 3 and 2 represent GPIO PA1. Bit 5 and 4 represent GPIO PA2. Bit 7 and 6 represent GPIO PA3. Bit 9 and 8 represent GPIO PA4. So this is where we're starting. From here onward until bit 17 and 16, which will represent GPIO PA8. Right? Now, if we want to write GPIO PA4 as an output, that means we only need to change bit 8 here. Bit 9 is going to remain 0, and bit 8 here is going to now turn to 1. That will then mean 01 introduce the GPIO port A pins. And we're going to do the same on all of these pins. And this will mean for PA8, we then need to write a 1 onto bit 16 and leave bit 17 a 0. And that will set it into output mode. So that's what we need to write into our code here. So now to do that, I'm going to just call the GPIO, and I'm going to call GPIO A, and I want to access the register for GPIO A, waiting for my IntelliSense to show the registers, and I'm going to take the GPIO model register, and I'm going to write my O, because I want to leave the rest of the stuff as is. We start tempering them. They will be in reset mode, which is 00. Then I'm going to put the selected bits that I want into output mode. Right. So we saw that for PA4, we only need to write bit 8 must turn into a 1 and leaving bit 9 to 0. So that means I'm going to also use a left shift, and I'm going to write in there a 1 unsigned long. So that basically means I'm shifting 8 times and writing a 1 into that bit and leave the other bit 0. Then I'm going to move with another OR operator into the next bit. So I'm going to just copy all of this and I'm going to paste it right there. So 1, 2, 3, 4, 5. So those are all my 5 pins. Let me just put a semicolon there. Then I need to move into the different pins. So let me just check to make sure here that we don't write different things here. So this will be pin 5. So that will be 10, 12, 14, and 16. Okay. We then need to change this into 10. The next one is going to be 12. And the next one is going to be 14. And this one is going to be 16 because this is pin 8. So that is pin 4, 5, 6, 7, and 8. Now, once we write these instructions, we're going to be setting these specific pins into output mode. But now we're not done yet. When you set the pin, just like when we set the old register into input mode, now we needed to take the selected pins, right? The selected pins and write a pull down to them because those are the pins that we're going to use. So we write a pull down into them. Now, unlike here, when we are doing setting pins as output mode, we don't have to use a pull down or a pull up. We can basically just have a no pull because it's the pin is not going to be influenced by external factor because it's not an input, it's an output. But we need to define which type of output we want it. So generally we set it into push-pull mode, right? So in order to set the pins into a push-pull mode, there is a different register you need to access and set a specific bit. So that register is called OTYPE register. So that is basically the output type mode register. So let's go and find the output type mode register into our reference manual. So we have to look OTYPR. There is OTYPR, so that is the output type register. Now, as you can see, this register is also supposed to be a 32-bit register, but actually only 16 bits are being used here. So now, what we're going to do here is look here. We've got so bit 31 and 16 are reserved, must be kept at reset value. So don't touch them, leave them at reset value, which is 0. Right now, bit 0 to 15. Now these bits, it says here, if you write a 0, it output push-pull, right? That's reset state. Now if you write a 1, it's going to be output open drain. So we want our pins to be in output push-pull. We don't want the open drain. So let's put it in output push-pull. So that basically means we need to write a 0 into these pins. Now to do that, we basically just need to shift because we know that we are using from pin 4, 5, 6, 7, 8. So it's going to be these 5 bits here. So we need to shift from here. We must shift 4 times. 1, 2, 3, 4. And when we get here, we need to write all of them 1, 1, 1, 1, 1. And then we need to invert them again to 0, 0, 0, 0. That way, whatever other value that's are going to be written into the registers, it's not going to be affected because we only targeting these selected bits to be set to 0 for output push-pull. Now to do that in our code, I'm going to come here and I'm going to call again GPIO A, and this time I'm calling the output type register. So that is this last one here, output type register. Now I take the register now because I want to reset the pin. So here I'm going to write a specific value that is going to turn the bits that I'm using, the selected bits, pin 4 up to pin 8. It's 5 bits. I need to turn them into 1 and then turn them to 0 again by inverting. So to do that, I need a specific value. Now we know that we're going to shift to the left 4 times. So if I take my calculator, so basically what we're going to do here, we're going to write 1, 1, 1, 1, 1, 5 times. And then we're shifting 4 times. Since we're shifting 4 times, then we need 4 zeros. 1, 2, 3, 4. And if you look here, the unsigned long value in decimal mode is going to be 496. We need to write into that register. Or in hexadecimal is going to be 1F. 1F. That's the value we need to write into that register. If I then do like this, I say 0, X, and 1F. This is hexadecimal. And I say UL. That means it's unsigned long, but in hexadecimal form. And I want to write that value by shifting 4 times. And it's going to be written into that register. But now, I cannot leave it like this because why? The story here is I'm going to write 111 into those bits. And then I'm going to invert it so that they can become 0. So to do that, I'm going to put an inversion symbol there. That's an inversion operator. So I'm going to invert it, and I'm going to use the AND operator instead of the OR operator, because I need to do the AND operation when I'm inverting so that I can keep those state back to 0. Right. Now, writing this will turn those specific bits into the push-pull type output. Right. Now we can then just remove all of this code because we don't need this code. Let's compile. All right, so we're done compiling. Now we can load it into our board just to see that we haven't broken our code yet. So I need to reset here. Okay, let me just reset there. Now let's write it into the board. Now, if these instructions are correct, we should get our LEDs to operate the functions of counting down and counting up, and also that sequence running like that we have already declared up there into our while loop. All right, now it is being written. It's being written, so we are waiting for the debugger to finish, and then we're going to test if everything is the same. Okay, so this is a good sign. Now I'm going to just start by pressing all of them. So the sequence is working. Okay, now let's set the count down. Countdown is also still working. Let's see the count up. Count up is also working still. So which means we've successfully also set the correct configuration into our LEDs pins and also the push buttons. All right, so now we are done here. So the next stage is basically just to start now changing this function here, because we can see we've got the GPIO read pin function and we've got a write pin function. So it's only these two functions that we are making use of here, the write pin and the read pin. Now we need to replace this function with the appropriate direct register access instruction so that we can get the same result.